Good morning, everyone. My name is Wang from East China University of Technology. The title of my talk today is Ultrathin Rare Earth Transition Metal Terbium Iron Cobalt Alloy Fumes with Perpendicular Magnetic Anisotropy. So the rare earth transition metal terbium iron cobalt alloy thin fumes can exhibit strong perpendicular magnetic anisotropy. So they are widely used in magnetic random access memory, spintronic devices, current-driven magnetic switching, and ultra-fast switching, and sky mills. So in the terbium iron cobalt alloys, the rare earth terbium and the transition metal iron cobalt sublattice moments are antiferromagnetically coupled. So there's a compensation point where the net magnetization is the lowest and the coercivity is the largest. So on the left side is transition metal rich, and on the right side it's rare earth rich. So this talk will be divided into 4 parts. The first part is on fabrication of terbium, iron, cobalt thin films by sputtering composite target methods. So the second part is on investigating effects of sputtering parameters and film thickness on magnetic properties of this terbium, iron, cobalt thin film. The third part is on investigating temperature-dependent magnetic, optical, and electrical properties of this terbium, iron, cobalt thin film. Finally, I will give a short summary. So the first part is on growth of this terbium, iron, cobalt thin films. So all the rare earth transition metal terbium, iron, cobalt thin films are sputtered in a rig with the base pressure of 6 times 10 to the minus 6 Pascal. So we designed the composite targets, which consist of iron cobalt disk and terbium chips. So from the magnetization hysteresis and the extraordinary Hall loops, the black curve here, we can see all the films have strong perpendicular anisotropy. So from the AFM image, we can see the roughness of this 35 nanometer thick film is around 0.18 nanometer, showing the film has smooth surface. So from the X-ray measurements, we can see no peak from the film can be detected. Only the silicon 400 peak from the substrate can be detected. So it tells us all the films are amorphous. So we investigate this sputtering power and the flow rate related magnetic properties of this terbium, iron, cobalt thin films. So we fabricated the thin films by varying the power and gas flow rate. So we can see there's a magnetic compensation region in middle. So on the left side is transition metal rich, on the right side is rare earth rich. We put all the data together, we plot this remelance ratio against the sputtering power and gas flow rate. So with increasing the power and the gas flow rate, we along the arrow here, so we can see the z-axis of the thin films changes from in-plane to canted, finally to out-of-plane direction. So the dotted region is magnetic compensation region. So on the left side is transition metal rich, on the right side is rare earth rich. So it tells us by proper combination of sputtering power and gas flow rate, the films with desired magnetic properties can be obtained. So we investigate the thin films with the thickness down to the 3.5 nanometer. So we fabricated the thin films on different substrates, such as this silicon and MgO coated silicon. So we plot all the data together. We found there's a critical thickness around this 14 nanometer thick. We can see the magnetization is the lowest and the coercivity is the largest. On the left side, the film is iron cobalt rich, and on the right side, the film is terbium rich. So compare this compensation point. So we can see this critical thickness is quite similar to this compensation point. So you can see on the left side, it's iron cobalt rich. On the right side, it's rare earth rich. And at this point value, you can see the magnetization is the lowest and the coercivity is the largest. So it tells us by using this critical thickness concept, we also can tune the magnetic properties of the terbium iron cobalt thin films, the property. So we designed two types of terbium iron cobalt thin films. So one is iron cobalt rich, the other is terbium rich. So all the films can exhibit strong perpendicular anisotropy. So we perform these thermomagnetic measurements. So we can see the compensation point is below room temperature. So it tells us the film is iron cobalt rich. So the bottom line, we can see the compensation temperature is above room temperature. So it confirms indeed the film is rich in terbium. Then we performed this temperature-dependent optical reflectivity and heat resistance measurements. So from the measurements, we can see there are two regions can be clearly distinguished. The structural relaxation in the lower temperature region and crystallization and oxidation in high temperature region. So by performing these varying weight rate measurements, so we can determine the transition temperature by using this Kissinger plot method. So we can determine the activation barrier. The activation barrier for this structural region, relaxation in this lower temperature region, are determined to be 1.13 eV and 1.03 eV respectively for the iron cobalt rich and the terbium rich samples. So the activation barrier for this crystallization and oxidation in high temperature region are determined to be 1.01 eV and 0.83 eV respectively for the iron cobalt rich and the terbium rich samples. So it tells us regarding the thermostatability, the iron cobalt rich sample is better than its terbium rich samples. So finally, I will give a short summary. The rare earth transition metal, terbium, iron cobalt thin films with good perpendicular magnetic anisotropy are spotted. The magnetic properties are shown to be adjusted by sputtering parameters, such as the sputtering power and gas flow rate. A change in polarity of the extraordinary Hall effect loops at a critical thickness of around 14 nanometers is observed. This corresponds to a transition from iron cobalt rich to terbium rich configuration. The magnetic properties of this ultra-thin terbium iron cobalt thin films are demonstrated to be adjusted simply by the film thickness using this critical thickness concept. The thermostatability of the terbium iron cobalt thin films rich in iron cobalt is confirmed to be better than those rich in terbium. So this is my group members and also several fundings to support this work. Thank you for your attention.